Let's follow along as the assembler processes our source file. The assembler maintains a symbol table that maps symbol names to their numeric values. Initially, the symbol table is loaded with mappings for all the register symbols. The assembler reads the source file line by line, defining symbols and labels, expanding macros, or evaluating expressions to generate bytes for the output array. Whenever the assembler encounters a use of a symbol or label, it's replaced by the corresponding numeric value found in the symbol table. The first line, n equals 12, defines the value of the symbol n to be 12, so the appropriate entry is made in the symbol table. Advancing to the next line, the assembler encounters an invocation of the addc macro with the arguments r31, n, and r1. As we'll see in a couple of slides, this triggers a series of nested macro expansions that eventually lead to generating a 32-bit value to be placed in memory location 0. The 32-bit value is formatted here to show the instruction fields, and the destination address is shown in brackets. The next instruction is processed in the same way, generating a second 32-bit word. On the fourth line, the label loop is defined to have the value of the location in memory that's about to be filled, in this case, location 8. So the appropriate entry is made in the symbol table, and the mul macro is expanded into the 32-bit word to be placed in location 8. The assembler processes the file line by line until it reaches the end of the file. Actually, the assembler makes two passes through the file. On the first pass, it loads the symbol table with the values from all the symbol and label definitions. Then, on the second pass, it generates the binary output. The two-pass approach allows a statement to refer to a symbol or label that is defined later in the file. For example, a forward branch instruction could refer to the label for an instruction later in the program. As we saw in the previous slide, there's nothing magic about the register symbols. They're just symbolic names for the values 0 through 31. So when processing addc, r31, and r1, UASM replaces the symbols with their values and actually expands addc 31, 12, 1. UASM is very simple. It simply replaces symbols with their values, expands macros, and evaluates expressions. So if you use a register symbol where a numeric value is expected, the value of the symbol is used as the numeric constant, probably not what the programmer intended. Similarly, if you use a symbol or expression where a register number is expected, the low-order 5 bits of the value is used as the register number. In this example, as the RB register number. Again, probably not what the programmer intended. The moral of the story is that when writing UASM assembly language programs, you have to keep your wits about you and recognize that the interpretation of an operand is determined by the opcode macro, not by the way you wrote the operand. Recall from Lecture 9 that branch instructions use the 16-bit constant field of the instruction to encode the address of the branch target as a word offset from the location of the branch instruction. Well, actually the offset is calculated from the instruction immediately following the branch, so an offset of -1 would refer to the branch itself. The calculation of the offset is a bit tedious to do by hand and would of course change if we added or removed instructions between the branch instruction and the branch target. Happily, macros for the branch instructions incorporate the necessary formula to compute the offset from the address of the branch and the address of the branch target. So we just specify the address of the branch target, usually with a label, and let UASM do the heavy lifting. Here we see that B&E branches backwards by 3 instructions. Remember to count from the instruction following the branch. So the offset is -3. The 16-bit 2's complement representation of -3 is the value placed in the constant field of the B&E instruction.